Hello and welcome. In this video, we're going to take a look at logarithmic functions, and they are the inverses of exponential functions. Now, we're going to just need a few of their most important properties in order to continue on with some of the calculus stuff that we're going to be needing soon. So let's take a look at those and see what kind of properties logarithmic functions have. Well, first of all, just a basic definition, the inverse of the exponential function a to the x is the logarithmic function log base a of x. And so by definition of inverses, we have that if, let's say, a to the x equals y, then equivalently log base a of y equals x. Now these are equivalent forms. So you can see here that when we're talking about exponential functions, we call a the base of the exponential functions, and a here is also the base of the logarithmic function. The thing that really changes is that the input of the exponential function is x, but the input of the logarithmic function is y. So they are inverses of each other because of that. And our most favorite exponential function, the sort of Goldilocks one, e to the x equals y. If we were to write that in logarithmic function form, it'd be log base y, or log base e y equals x. But we really, oh gosh, that's gross. Log e y, it almost looks like it should be a word. Well, let's avoid that. All right, let's cross that out. What we actually use instead of log base ey is we just use what we call the natural logarithmic function. Ln, if you want. Ln of y equals x is the actual way that we write the inverse of the e to the x function. Now, we can take a look at any base. Let's start off with some exponential functions that you can do pretty easily without the aid of a calculator. For instance, we know that if we have a function like 3 to the y, let's say, or maybe 3 to the x equals 27, you can probably guess what that value of x is. 3 to what power equals 27? Well, that's equivalent to saying that x is equal to the log base 3 of 27. Log base 3 of 27 is the value 3, because we know that 3 cubed is 27. That's the value of x. All right, but we can try a couple other examples. For instance, maybe we have 8 to the power x equals 2. Okay, now 8 raised to what power equals 2? That might be a little bit trickier. You can't be squaring or cubing 8 because that gets bigger. You're going to have x be a fraction. Now, if you wanted to translate that into logarithmic form, then that value of x would simply be log base 8 of 2. And it may take a little bit of time for you to kind of guess that one. Maybe you already have it handy, but the cubed root of 8 is equal to 2, or 8 to the 1/3 is equal to 2. So that is the value of x. And in fact, log base 8 of 2 is simply the value of 1/3. So really, these logarithms are kind of useful when we're trying to solve equations with an unknown in the exponent. Now, one more example, if we have e to the power x equals 8, then x is simply equal to the natural logarithm, that's base e, of 8. And of course, that may not work as a nice number, but now if you take a look at your calculator, you have a natural logarithm button. And you can just type in logarithm of 8, and you can get that into a decimal format. And you can confirm that that is the correct value of x by hitting the e to the x button right afterwards. E to that decimal should equal 8 if you've got the right value. All right, now that you know that they are inverses by that definition, now we can apply the ideas in the last video about inverses to figure out what the graph of logarithms look like, and particularly the graph of the natural logarithmic function. Now, hopefully you've got the idea of the graph of any exponential function where the base is greater than 1 as being this exponential growth curve. And e to the x is just one of the many exponential growth curves that increase as you go further to the right and increases quickly. Now, because the natural logarithm function is the inverse of e to the x, then what we need is a 45-degree line. And that 45-degree line has the equation y equals x, because it has a slope of 1 and goes to the origin. So we can put that on the graph here as well. And you can try pausing this video if you like, just to see if you can graph this sketch, or sketch the function y equals the natural log of x by reflecting the red curve over that diagonal line. Now, you can try it out. Hopefully you can check your answer here. Reversing that coordinate, you know that this graph should go through the coordinates 1, 0. And the reflection looks something like this. And there is the graph of y equals the natural logarithm of x. Now, what about some properties of logarithms? We know we already have the domain and range of the exponential function. What are the domain and range of the natural logarithmic function? Looking at the graph, we can already see from a previous video, we see that the e to the x has a domain of all real numbers. And if you want to write that as just r, that's great. Or you can use interval notation. Now the range is only going to be positive values of y. Now, the blue graph, it takes the range of e to the x and it becomes the domain of ln x. So you can even see this from the graph that ln x has only the domain of positive numbers. You can't take logarithms of negatives and you can't take logarithms of 0. And the range, well, even though this blue graph seems to actually grow slowly to the right and actually get slower the farther you go, it does continue to increase as far as you want. And so the y values can go as high as you like or as low as you like. And that means that you have a range of all real numbers. This is a very common logarithm, the natural logarithm of x. But in other courses, you may be using logarithms of base 10 frequently. So I'll just make a mention here that in mathematics, our favorite logarithm is the natural logarithm of x. But in other courses, like physics, when you're talking about, let's say, decibels, if you want to look at the intensity of sound, it uses logarithms with base 10. In chemistry, if you want to look at pH, that's using logarithms of base 10. In other sciences, it's probably one of the more common ones. Like, for instance, the Richter scale, that also uses logarithms of base 10. And rather than always writing log with little base 10 on there, if you just have log of x, then that is taken to be a base of 10 without having to write it. That's called the common logarithm, so base 10. Now for all logarithms, whether you're talking about our favorite ln, or if you're using any other base, there are some cancellation laws and some other properties of simplifying or expanding logarithms that we need to know. Let's start off with the cancellation laws. For the cancellation laws, it kind of works like you'd expect that the cubed root cancels something cubed. The logarithm of base a cancels a to the power of something. And so our first rule here, especially if you just want to take a look at the natural exponential function in red here, the natural logarithm of e to the power x is simply x. There is a slight deviation from what you'd expect when you actually reverse the order of the two functions. E to the power of the natural logarithm of x. They cancel out as well, but remember that in this case the logarithm is being applied first, so x needs to be in the domain of the logarithmic function. It has to be a number from 0 to infinity, not including 0. Okay, now next up there are a few other properties to take logarithmic functions involving a product or powers or a quotient and simplifying them. And here are three of those properties. So the first one is if we have the logarithm of a product. So two things that are just factors forming a product inside a logarithm, then we can split that up. But the two factors in that product become separate logarithms added together. Now, if you want to see an example using the natural logarithmic function, we can have something like the natural logarithm of x squared y. And you could write that instead as the natural logarithm of x squared plus the natural logarithm of y. And if you have more than two factors, you can continue to split them up and have more and more of these individual logarithms added together. The next property, number 2, is if you have a quotient inside a logarithm, and then you can split up that quotient and have the entire numerator in one separate logarithm, and you subtract the entire denominator in a separate logarithm. If you want to see an example with natural logarithms, we can have 3x over y and split that up into the natural logarithm of 3x minus the natural logarithm of y. And you see that because I have the logarithm of 3x, I can also continue to expand that even further, if you like, into the logarithm of 3 plus the logarithm of x minus the logarithm of y. So that's actually applying rule number 2 and 1. And the third property is if you have exponents inside the logarithm, then as long as that exponent is applied to everything in the logarithm, then that exponent can be sort of removed from the logarithm and placed out front as a factor of the logarithm. So if I have the logarithm of x squared y to the power 6, then maybe what I'll do is I'll find a common power of the whole thing and write this as xy to the power 3 all squared, and I'll move that 2 out in front of the logarithm and call this 2 times the logarithm of xy cubed. Now that could be as far as you need to go, but you can continue to apply further rules after that. We can then take that 2 and split the logarithm out into two separate logarithms, the logarithm of x plus the logarithm of y cubed. And once we get that far, we see that everything in the second logarithm all has a common power, and you can continue. And once you're all done, it's probably best to distribute that too. 2 times the logarithm of x plus we have 6 times the logarithm of y. And that might not be the only way of simplifying it, at least not the only order of applying those rules. Try applying the rules in your own order and maybe splitting it up using rule number 1 first and then rule number 3, and you should get exactly the same thing. So long as you apply these properties correctly to products, quotients, and exponents, you will get the correct answer. Now just be really careful with those last 3 properties, because oftentimes I see mistakes where you have the logarithm of x plus y and you try to split that up. That doesn't work. You'll need to have the logarithm of a product to split into addition. Now it works in reverse. If you have ln x plus ln y, you can combine those together into ln xy. It really depends on whether you want fewer logarithms with a more complicated operand inside, or do you want to take a single logarithm with a very complicated operand inside and split it up into simple logarithms. That's a very handy use of logarithms that we'll see later on in chapter 3, is when you have just a huge mess of products, quotients, and powers. You might be able to take the logarithm as a tool for splitting it up. But that's for a video quite some time for now. In our next video, I think we're probably going to be looking at inverse trigonometric functions, which, spoiler alert, are pretty nasty. But that's for the next video, and I'll see you then.